EXCITE is a multi-body dynamic software tool calculating in the transient or in the time domain, utilizing rigid or flexible bodies. EXCITE has three main application fields: durability and strength of various components, NVH from system dynamics to acoustics, and EHD contact investigations, more specifically bearing evaluation, failure mechanisms, wear, and friction. My name is Brian McCaskey, and I am a software support engineer for AVL EXCITE. What I would like to do is to provide you with an overview of EXCITE Power Unit. What you see on the screen is the graphic user interface. On the left-hand side, we have our element tree, which shows the various bodies and joints that are available to use in EXCITE. We also have a 2D view window, and this is where we will work on setting up the model. I'm going to be showing you an inline-four engine. I'm going to begin by inserting the various bodies and joints into the 2D workspace. I double-click, and I insert my body into the workspace. I'm also going to add a connecting rod. And then finally, I'm going to select a radial slider bearing, select the connection tool, and connect the two bodies together. I will continue this process until I have a representation of my simulation model. As you can see, I now have my inline-four engine set up with the various components. If I select any one of the bodies or the joints, I double-click on them in order to open up the properties. Additionally, once I define my FE model, I can then go to the 3D view, and I can see a visualization of the system as it is presented. It's very simple to parameterize and set up cases for simulation. We simply come to the parameter window, and we can add parameters, and then we can come to the Case Explorer, and we can specify the different speeds that we're going to run, as well as any other data that we would like to change. I come to the Simulation menu, and I come to the Simulation Control. And here is where I define how many cycles I'll be running. I specify my step size, as well as some additional data for the load reference and for the data storage. I will do the same for the result data. I specify the number of cycles that I would like to examine at the end of the simulation, and then I can select the results that I would like to have shown. Additionally, we offer standard reports for the single cases as well as the entire case set. There are several plot types available. Once I have set up my simulation, then I can go ahead and I can run it. I select the number of cases I would like to run, I select the tasks I would like to run, and then I click the Run button. I now have results that I can examine. So I'm opening Impress Chart, which is our 2D post-processing tool. When I do so, I can see the cases that I have run in this simulation. I can click the Insert Layer tool, and I can expand any one of the cases and any one of the bodies to show a result I would like to look at. And I can do this for as many or as few results as I would like to see. In this way, I can slowly build up a report of my own that would encompass all of the results that are specific to my analysis. We have the standard report for 3000 RPM, and based on the input that we specified, there are 22 plots that are available to us. The first plot is showing the angular velocity and the angular acceleration of the crankshaft. We also can look at the motion amplitudes of any node, as well as the velocities or even the accelerations if desired. Here's a sample of the torsional vibration at the front of the crankshaft. Additionally, we have the case set report, which provides us with data for the entire speed range that we have run. Here we have the peak firing pressure shown for the entire speed range from 1,500 RPM to 4,000 RPM. Additionally, I can go back to the result for the crank node that I was looking at, and I can now see a plot showing the displacement magnitude versus speed over the frequency range. We also offer order tracking. The same applies for the velocity plot. We also can visualize the max forces and max moment, as well as the bearing load envelope. And once again, the torsional vibration analysis for the front of the crankshaft. Next, I'm going to show you our 3D post-processing tool called Impress 3D. Impress 3D allows us to visualize any sort of result that's available to us, such as constraint forces, loads, displacements on the condensed mesh that is shown here. So I've already preloaded the constraint force results for this engine, and I'm just going to push the play button. As you can see, as the connecting rod is moving down the cylinder, we have some constraint forces that are appearing on the liner. You can see the firing of cylinder number 3. We can also see the reaction at the engine mounts as well. And finally, the bearing constraint forces. Thank you for watching. Check out the other videos in our YouTube series. Also, visit our website at www.avl.com.